syntactic ambiguity. Huh? Well, syntax is the system of how we sort words into statements that can be clearly understood. If you are familiar with the movie Star Wars and the character of Yoda, he might have said something along the lines of, "Problems have I, English syntax forming." And while you can still probably understand that sentence, you can see how it is perhaps a little bit more difficult to understand someone if their syntax is bad. And this is why sometimes if you learn a new language with very different grammar, you can find yourself not being understood even if you're using all the right words, because you might be using them in the wrong order. You're using the wrong syntax. If something is ambiguous, then it may have two or more different meanings, and so it's possible to understand it in other ways. So something is syntactically ambiguous if you can understand it in different ways because of the way it is written grammatically. So in language, this is often due to unclear punctuation. For example, I will run 6 kilometers, or I will play football, and I will eat pizza. Is this sentence a disjunction or a conjunction? We can see or there, suggesting it's a disjunction. However, we can also see and there, suggesting that it's a conjunction. How are we supposed to work this out? Well, we do so by using the principle of the dominance of connectives. And that means that we can use mathematical techniques to avoid ambiguity, especially parentheses or brackets as they are sometimes known. So these work in a similar but not identical way to parentheses in algebraic mathematics. Simple statements represented as letters can be joined together using the symbols we saw, but we then might need to use a bracket to show us what we want to do first. For example, let's say that in the example on the previous slide, P equals I will run 6 kilometers, Q is I will play football, and R is I will eat pizza. So we can either write this as a disjunction, P or Q and R, and there we put the conjunction in brackets, and that shows that it's the disjunction outside the brackets which really is the kind of statement we're looking at. If we're writing that statement out, a comma is sufficient to make our meaning clear. I will run 6 kilometers, or I will play football and eat pizza. On the other hand, this statement might be a conjunction, P or Q and R. So in this case, the comma is put just before the and. I will run 6 kilometers, or I will play football, and then I will eat pizza. Either way, it suggests. So as we can see, the parenthesis becomes a single object in the final statement. So in the first example, we are using a disjunction, so it's P or the bracket. In the second case, where it is a conjunction, it is the bracket and R. Everything inside the bracket, from the point of view of the whole statement, counts as a single logical object. And that is why we resolve the bracket first, just as we do in algebraic mathematics. So now we know how to use brackets on their own, but there is also an order for the dominance of connectives anyway. In any normal case where there are no brackets, the biconditional will be the most dominant connective. Following that, the conditional will be the next most dominant connective. After that come disjunctions and conjunctions, and then finally negations. So the most dominant is the biconditional and the least dominant is the negation. Conjunctions and disjunctions have equal logical weight, so if you are using them together, then you must use parentheses to correctly denote your meaning. And then any symbol outside a parenthesis outranks any symbol inside the parentheses. So for example, not P conditional Q is a negation because the conditional is inside the brackets and the negation is outside the brackets. So the conditional is made less dominant because it is inside those brackets. Just a final side note on connectives. We have two different types of connective: binary operators, which join two statements together, and unary operators, such as not, that act on a single statement. So it's not a connective in that it doesn't connect things together. On the other hand, you might say it does connect to a statement and it changes the meaning of the statement it connects to. So for example, Dave is here and Alan is here. That is two statements connected by a binary operator. Mavis is not here. That is just one statement acted on by a unary operator. It does not make any sense to say Mavis is and here or something along those lines. You cannot use a binary operator on a single statement in this way. So now we come on to truth tables. So when we use logic, as we said at the beginning, truth values are the foundations of any meaning that we get out of statements. So if we think about a single simple statement, like today is Thursday, then it is usually very easy to assign a truth value from our background knowledge. In this case, we will probably know that it either is or is not Thursday today. However, when we want to look at many different outcomes to more complex logical structures, it's not always this simple, and a truth table is a convenient and fairly quick way to compare all the different possible combinations of truth inputs to see what the outputs of your logical function are. Truth tables are really showing us the mechanics of logic in action, and over the next few slides we're going to look at the basic truth tables of the basic logical functions. And if you want to be good at logic, then you will really need to have memorized the truth tables of these basic logical functions so that you can quickly combine them into more complex forms. So let's look at the negation, the easiest form of truth table to start with. A negation simply reverses the truth value of the statement that is our input. So if our input is true, the negation is false, and vice versa. And here's the truth table for a negation. So a negation, as we saw, is a unary operator. It can only act on a single statement. So our truth table simply has a column for P, and if P is true, then not P is false, and if P is false, then not P is true. This is the most straightforward form of truth table that we can design. So when we want to construct truth tables, we will see that there are sometimes different sizes of truth table. How do we know how many outcomes there are? Well, it's actually quite easy. If we have more than just a simple statement on a unary operator, then we can say that any compound statement with n simple statements will have 2 to the power of n different true or false combinations.